All right, let's get right into it. We've all felt the ground shake, or at least seen the headlines, but what's really going on down there? Well, today, we're going to go on a little journey, all the way from the fiery center of our planet, through billions of years of geology, and right up to the science that keeps our buildings from falling down.
You know, for most of human history, earthquakes were just the stuff of myth. You had angry gods, giant turtles, you name it. The ancient Greeks, they figured Poseidon was just having a bad day and smacking the seafloor with his trident. So the real story here is how we went from tales like that to the super precise science of seismology. It's all about uncovering the absolutely massive forces at play right under our feet.
So, scientifically, what even is an earthquake? It's just a sudden, incredibly rapid release of energy. And to talk about it like a pro, you only need 2 words to start. The hypocenter. That's the real ground zero, deep inside the Earth's crust where the rupture begins. And the epicenter? That's the spot you always hear about on the news. It's just the point on the surface directly above the hypocenter. Simple, right? But so crucial.
Okay, so to really understand where that energy comes from, we can't stay on the surface. We have to dive deep, deep inside the planet and take a look at the massive, restless engine that powers every single earthquake.
Our journey starts right here, on the crust. It's this super thin, brittle shell that we live on. Honestly, think of it like the skin of an apple. It's incredibly thin compared to the rest, and it's where all the action that we actually experience happens.
Now, you go a layer deeper, and you hit the mantle. And this is where things get wild. It's solid rock, okay? But, and this is a big but, over millions and millions of years, it actually flows, kind of like a ridiculously thick, slow-moving liquid. This slow churning motion, it's the key to everything. And at the very center of it all, you've got the core, a liquid outer core of iron and nickel sloshing around a solid inner core that's as hot as the surface of the sun. Now, obviously we've never been there, but we know it's liquid because of how earthquake waves travel through it, or more importantly, how some waves don't. And we'll get to that in just a bit. So all those layers, they bring us to the single biggest idea in all of geology, plate tectonics. See, our brittle crust isn't one solid piece. It's shattered into these massive plates. And these plates are literally floating on top of that slowly flowing mantle. They're constantly moving, bumping, and grinding against each other. And it's right there, at the boundaries where they meet, that's where the vast majority of earthquakes are born. So we know the plates are moving, but how does that super slow grind, we're talking centimeters per year, turn into a sudden, violent, catastrophic shake? To see that, we've got to zoom way in on a fault line and look for the snapping point. And it's all explained by this beautiful idea called the elastic rebound theory. Here's how it works. Think about bending a wooden ruler. As the tectonic plates push past each other, the rock along the fault gets stuck, and it starts to bend into form, storing up energy just like that ruler. It bends, and it stores more and more energy, until the stress is just too much for the rock to handle. And snap! The fault ruptures, the rocks violently snap back to their original shape, and all that stored energy is released at once. That snap, that is the earthquake.
So once all that energy is released, it doesn't just hang out at the hypocenter. Nope, it travels outward in every direction, like ripples in a pond, in the form of powerful seismic waves. The first waves to show up are called body waves because they travel through the body of the Earth. First, you get P waves for primary. They're the fastest, and they're compression waves. They push and pull the rock as they go. Then come the S waves for secondary. They're slower, and they move the rock side to side. But here's the really cool part. Look at that last row. S waves can only travel through solids. The fact that they just stop and disappear when they hit the Earth's core was the smoking gun, the absolute proof that the outer core has to be liquid. Pretty neat, huh? But, you know, the waves that cause almost all of the damage, they're actually the surface waves. They're the slowest of the bunch, but they have the biggest motion. They create that horrifying rolling and side-to-side lurching that is just so destructive to our buildings. This is what people really feel during a big one.
All right, let's clear something up. When we talk about earthquakes, you always hear 2 words thrown around, magnitude and intensity. They sound kind of the same, but they measure 2 completely different things, and the difference is crucial. Let's break it down. So here's the bottom line, the thing to remember. Magnitude is the cause. It's one single number, measuring the total energy the earthquake released way down at the hypocenter. Intensity, on the other hand, is the effect. It describes how much shaking and damage happened at one specific spot on the surface. So an earthquake has only one magnitude, but it can have many different intensities depending on how far away you are.
And there's one more thing about that magnitude scale you absolutely have to know. It's not a normal scale. It's logarithmic. So what does logarithmic actually mean? Well, it means for every single whole number you go up on the scale, say from a magnitude 6 to a magnitude 7, the amount of energy released increases by a factor of about 32. Let me say that again. 32 times more energy? So a 7 isn't just a little bigger than a 6. It is a completely different beast. That difference is just staggering.
Okay, so we've got the science down. Let's bring this all back to the surface. What does all this incredible power mean for us? And how in the world do we survive living on such a dynamic, restless planet?
Now check this out, because this might surprise you. You'd think most of the damage and loss comes from the shaking itself, right? And yeah, about 60% does. But a massive 40%, almost half, comes from what the shaking triggers after the main event is over. And that huge 40% comes from these absolutely devastating secondary hazards. We're talking about tsunamis from underwater quakes, landslides in hilly areas, massive fires from broken gas lines, and this terrifying thing called liquefaction, where solid ground literally turns into a destructive liquid soup for a few minutes. And you know, all of this, it brings us to maybe the most important and sobering takeaway for our own safety. The ground shaking itself rarely kills anyone. Earthquakes don't kill people. Poorly constructed, collapsing buildings do. The difference between a major disaster and a scary inconvenience, more often than not, comes down to engineering.
So this all leads to the one question everybody always asks. With all this amazing science, can we please just predict them already?
And the answer, I'm sorry to say, is a firm no. Prediction, stating the exact time, place, and size of a future quake, is still science fiction. But what we can do, and what we're getting better at every year, is forecasting. That means calculating the probability of a quake in an area over decades. And even better, we have early warning systems. These don't predict a quake, they detect one that has just started and send out an alert that travels faster than the shaking, giving people precious seconds to drop, cover, and hold on. So in the end, living safely on this restless planet isn't about having a crystal ball. It's about having something much more powerful, understanding the forces at play, engineering our world to be resilient, and preparing ourselves with knowledge. And that, right there, is how we turn this incredible science into survival.